So today I'm going to continue some discussion of cutoff, but then switch topics to rate of escape and relating that to mixing as well. So here is one very simple example of cutoff, but it already illustrates one interesting phenomenon. So suppose we have a line segment, and we move to the right with probability p, to the left with probability 1 minus p. So this chain could be periodic. So we always look at the lazy version, namely with probability half we stay in place, and with probability half p we move to the right, half 1 minus p we move to the left. And so we're going to take p to be bigger than a half, so there is a bias to the right. And so in all these things there is a, so if when we're doing the lazy version, there's always a factor of 2 that is sometimes implicit here. So the time to need, so the hitting time from the left to the right will be n over beta, but again, for the lazy version, you have to double that. And so the actual time to take into mix by the lazy version is twice n over beta, where beta is the drift. So in this case, because almost all the stationary measure is concentrated on the right, so the stationary measure grows by a factor p over 1 minus p as you move from left to right, almost all of it is concentrated in the vertices on the rightmost side, namely, if I take the k vertices that are on the right, then the remaining stationary measure is exponentially small in k. And from that, you easily deduce that the mixing time is equivalent to the hitting time from the left to the right. And this is classical to estimate using, say, the central limit theorem, which will hold. So you have to take into account the reflections here and here, but you can still deduce that the mixing time is n over beta, again, times 2 because of the laziness. So here is an occasion for one nice exercise. Show the mixing time in L2 is so I'll write T mix L2 of epsilon is asymptotic to some C constants times n, where C is strictly bigger than 2 over beta. So in other words, while mixing time here is determined by the drift, so it's n over beta, again, times 2, if you want to mix in L2, it takes strictly longer than to mix in total variation. Note that there is cutoff here, namely this both in L1 and in L2. So, so in L1, T mix of epsilon for total variation is asymptotic to n over beta, again, times 2. This is true as n tends to infinity for any epsilon. So the first order asymptotics don't depend on epsilon. But if you look at the L2 mixing time, there is again cutoff, so it's asymptotic to a constant n, but it takes strictly longer. So this very simple example already illustrates that L2, which is the most often the most convenient analytically to analyze? Well, this example is very simple in L1, but in richer settings, L2 is very easy, but you have to be aware that in settings of bounded degree, like this one, L2 mixing tends to happen later than L1. And you see striking examples of this in Eyal's last talk, I believe. Okay, so with that comment, so I'm going to maybe skip this discussion of trees since I left it as an exercise, but again say that maybe I'll say the word. So I stated the exercise, and I think Eyal gave you the same exercise, to take a tree with n nodes. So n is equivalent up to, well, it's about 2 to the k, where k is this depth. And it's twice that minus 1. And the question is to show there's no cutoff. So one way to show there's no cutoff is to show that T-mix T-mix of epsilon behaves like some constant that depends on epsilon times n, but let's not worry about T-mix epsilon. So T-mix of a quarter, show that that is equivalent to n, and show that the relaxation time is also equivalent to n. And this is, again, lazy, simple random walk on this tree. And this is a binary finite tree of depth k. All right, so the relaxation time is equivalent to the number of vertices. The mixing time is also equivalent to the number of vertices. And because of the necessary condition for cutoff, you deduce that this case doesn't have cutoff or pre-cutoff. Okay, so often people confuse trees and expanders because the infinite tree is in a sense an expander, but finite trees are very different from expanders. And so while on many expanders will have cutoff, on the regular trees we won't. Okay, so one problem that is still open is to characterize cutoff in a way where we can determine it without very precise calculations. So we see that in this example, just by estimating mixing time and relaxation time up to constant, we can determine that there's no cutoff. So to rule out cutoff, we can do rather crude estimates where we lose constants. But to prove cutoff, we don't have yet a general method that allow us to do crude estimates, say the mixing time is this order, the relaxation time is that order, and because of that we deduce that there necessarily is cutoff. So for positive results we need something more. So that's a problem that has consumed us for some years. One result in this direction, which I will say more in the last lecture, is with Ridi Basu and Jonathan Hermon. And this relates cutoff in the sense of mixing to cutoff in the sense of hitting large sets. So analogously to the mixing time, which says how close we get in total variation to a distribution, we can look at hitting times of large sets. So formally hit half of epsilon is the first time where for any starting point and for any target set A of stationary measure at least a half, the probability that we still haven't hit it, the tail of the hitting probability, is less than epsilon. So see, it's very close to the notion of a mixing time, but the difference is instead of asking for distributions, we're asking for tails of heating times. And as is noted here, the point of using this definition is that it allowed us to prove that in the class of trees, the conjecture of the conjecture that Tmax over Trel goes to infinity, this always necessary condition is actually sufficient for cutoff in trees. An earlier result in this direction is with Jian Ding and Eyal. We showed that on I think this okay. We showed that on for birth and death chains, the condition is sufficient. So this goes to infinity if and only if if and only if there is cutoff. And the same thing was proved earlier for separation. By Diaconis and Salovkost. So the historical story goes the other way from what I wrote it. So the first result is Diaconis Salovkost, who considered not the total variation distance, but the separation distance that I described last time, and showed that on that distance, the conjecture holds. If this ratio goes to infinity, then that's equivalent to cutoff. And then in this paper with Jian Ding and Eyal, we showed that on birth and death chain, again, both of these results are for birth and death chains, so those are just Markov chains that move on a path. At any point, they can go left, right, or stay in place, but it's not simple random walk. So you have arbitrary transition probabilities to the left, to the right, and staying in place. And in all these cases, to avoid periodicity, let's assume laziness in all these cases. Okay, so those were the first two results. And in particular, these results show that for birth and death chains, cutoff in separation is equivalent to cutoff in total variation. And then in this later work with Basso and Hermon, we showed the same thing holds for trees. So by trees, I mean now not just simple random walk on trees, but any Markov chain where the underlying graph of allowed transitions is a tree. And it doesn't have to be a regular tree. So you have an arbitrary finite tree, and the only assumption is that the transition probabilities are along the edges of the trees, but they could be arbitrary. Any chain like that is reversible. So again, in this class, there are no counterexamples. Mixing over relaxation going to infinity implies cutoff. And one can somewhat generalize this. So both in this paper, both in birth and death chains and for trees, if instead of going to neighbors, you allow some bounded jumps, then you can still get the same result. So there is some regularity assumption there, so I don't discuss that generalization in detail, but it can be generalized from nearest neighbor to some bounded jumps. Okay, so the technique of this proof relies on this notion of cutoff for hitting times. So there is a hitting cutoff for a family of lazy reversible chains if and only if the difference hit half of epsilon and hit half of 1 minus epsilon is little o of hit half, say, of a quarter. This is an analog of the definition of cutoff, but now for hitting times. And again, the basic result is that it's enough to verify this type of modified type of cutoff to deduce, in fact, it's equivalent to cutoff for mixing, which is what we usually care about. The reason this sometimes, so this looks like, okay, we replaced one definition by another definition. Why is this helpful? The reason is that in some cases, we can more easily identify what are the sets that's hardest to hit, as opposed to what are the sets that take the longest to mix. So trees is one such case. And I won't give you the details of this proof, but I just want to illustrate what are the sets that are hard to hit in a tree. So given that I have an arbitrary tree, there's always a notion of a central vertex. So what's a... So a vertex is central. What does that mean? It means that if I take the tree T and remove the vertex V, so I take tree and just remove the vertex V together with the edges adjacent to it, this, of course, will be a union of some new trees, which are the connected components remaining. They correspond to the degree of this vertex. And all of these should have stationary measure less than half less than half the total stationary measure, which was 1. So we want that when we remove it, no piece of the tree will be larger than half the tree. So they're always, so here's one kind of easy, fun exercise if you haven't seen it. Show that for any tree, so this is a finite tree, pi here, of course, is just proportional to the degrees. So the stationary measure for simple random walk is given by the degrees. In general, we're talking about a tree with some transition probabilities, and pi is a stationary distribution for that. It's true, in that generality. It's true really for any measure on the tree that there exists a central vertex. Can there be more than one?
Yes.
Can there be more than two? No, at most two. So if you have a tree like this, then both of these are central vertices, but so there exists a central vertex and at most two. Again, when
They're adjacent?
what?
They're necessarily
They are necessarily adjacent, yes. So here is one exercise, and then the kind of morally what drives these proofs is the fact that the sets that are hardest to hit are the sets that are hiding behind the central vertex. So if I have, so for every central vertex and every starting point x, I can look at the set of points that hide behind the central vertex. So it could be several components here. So for instance, if this is x, then these two components are hidden from x or separated by the central vertex from x. So this set, which includes the central vertex V and these components that are not the component of X, form a large set of measure at least a half. And this type of set is the hardest to hit in a tree. And that's, so because we can identify, so that requires proof, but because we can identify these sets that are hardest to hit, we can analyze trees better than other graphs. Questions? Okay, so I want to say something about product chains, which are an important class. So if I have n different chains, often we take them to be copies of the same chain like we do in the hypercube. Then we can define several natural chains on the product space. And one chain is choose a coordinate at random and then move in that coordinate. So formally, this is given by, so if we had original transition kernels pi on the ith chain, then this lifts to the product space. So pi tilde will be a transition kernel which only moves the ith coordinate and keeps the other coordinates in place. And then the chain is just an average of these pi tilde. Formally, what this means, we have n coordinates. Each one is a chain in its own right. We choose one of these uniformly. Of course, you could use other weights. And then we move in that chain. So this is a type of chain that's often used. And here is one result. There are many versions of this result. I think the earliest is due to Diaconis-Salofkos 96. The version I state here is actually written here for the continuous time version of the chain. I'll explain. And there's a very nice version in the work of Eyal Lubetsky and Alan Sly, and also in the work of Lacroix that I'll come to. So the version I'm stating here is actually a little bit different because this is the version that's easiest to prove. It involves, instead of the discrete time chain, the closely related continuous time chain, where instead of doing what I told you, where we choose a coordinate random and move that, we do this with, we wait an exponential time, and then, exponential time with mean 1, and then we choose one of those coordinates. So it's equivalent to giving an exponential clock of mean n to each of the coordinates and having them all move independently. So that's, continuous time is, in some respects a little easier than discrete time because it creates some more independence. But the type of results remains the same. I'm just stating the continuous one because that's the easiest to prove. And the basic thing you'll see here is the generalization of the hypercube result. So remember, in the hypercube, we had a mixing time of n log n over 2 with cutoff. So in general, if you take a fixed chain and take the nth power of that chain, that always will have cutoff. And we can pinpoint where it is. So the cutoff time is is n log n. Instead of n log n over 2, there is another factor gamma, which is the spectral gap of the underlying chain in one coordinate. So for the hypercube, the underlying chain was very simple. It was a two-state chain where in time 1, you just move to the uniform distribution, right? So because it's lazy, so at time 1. So that chain has spectral gap, has eigenvalues just 1 and 0. So spectral gap of 1. So in that chain, you get half n log n. The generalization here is you still get the half n log n, but there is this factor 1 over gamma, which comes from the relaxation time of the individual coordinates. So you see that when I take a large product, the mixing time of the large product is not determined by the mixing time of the individual coordinates, but rather by the relaxation time. So this comes back to the distinction between classical Markov chain analysis and the more modern one. So in the classical one, one took a fixed chain, maybe with 1,000,000 states, maybe with 100 states, and drove time to infinity. And then the asymptotics really depended on the highest eigenvalue. In the more modern theory, modern here goes back to 1980, we think of a growing sequence of chains, and we're just interested to drive the total variation distance down to some fixed epsilon, not to really close to 0. And then the mixing time is not determined just by the highest eigenvalue. However, in this setting, when we take a large product, in order to get the total variation distance small on the large product, you really have to drive it to very small on each coordinate. Hence, the modern theory on the large product reduces to the classical theory on each coordinate. That's why the determining factor is the relaxation time in each coordinate rather than the mixing time in each coordinate. Okay, again, this theorem, so again, in the Markov chain book, you can find the proof of this. So I'm not going to give it here in detail, but I wanted to explain where it comes from. One.
Sorry, here it's read n chains run independently.
What?
It's like n independent chains.
Yes.
Run independently.
Yes.
Each other with this exponential time.
Yes, exactly. Now, the way I stated it here, I wanted to keep the correspondence with the discrete time chain so that each coordinate had a clock of mean n. Often when we go to continuous time, we then also speed up. So we make each coordinate move with mean 1 or rate 1. And then you will lose a factor n everywhere here in the mixing times. So just be aware, when people talk about continuous time, often they do this rescaling, which I haven't done here. Now, one very, very nice and very general theorem by Chen and Salof-Kost says that if I have a discrete time lazy chain or a continuous time chain, they have cutoff together. So you can pass from one to the other. And prove whichever version is more convenient in an application. One direction of this is very easy, or I should say one bound in this direction. So if you can, it's easy given the lazy chain upper bound, it's easy to obtain a continuous time upper bound because continuous time chain can be seen as an average of the lazy chain. But the other direction is non-trivial. It's kind of a Tauberian theorem. So an abelian theorem is one that involves averaging. It's usually easier. So that's passage from the lazy or discrete time chain to the continuous time chain is an abelian theorem. It's very easy. This was everybody knew this before that paper. The non-trivial thing here is to go the other way and to go from a mixing of the upper bound and a mixing of continuous time chain to the lazy chain, which involves some. It's an analog of a Tauberian theorem or depoissonization. I should say that for reversible chains, we can go further. And so in work with Jonathan Hermon, we proved the conjecture of Aldos, which says that for discrete time chains, instead of doing the usual laziness device to get rid of periodicity, you could just do one lazy step in the beginning. So again, this is only for reversible chains. Instead of looking at mixing time of the lazy chain or of the continuous time chain, you can just take one lazy step in the beginning, and then all the rest are just steps of the discrete time chain, and that one lazy step is enough to kill all the possible periodicity, and you get a cutoff in this revised one-step lazy chain if and only you have cutoff in the continuous and the lazy chains. So this is only true for reversible chains, because for reversible chains, the only real type of periodicity you can get has period 2. Of course, in non-reversible chains, you can get other periods, and this one lazy step is not going to do it. Okay. So So one other thing I will comment on is that the proofs for the continuous, when one works with product chains, there's another metric I didn't discuss, which is extremely useful, which is the Hellinger distance, which is written here again in our Markov chain book and in many other sources. You can find more discussion of this. But the key of the Hellinger distance is that it behaves very well on products, much better than total variation, and it can be bounded above and below by the total variation distance. So I'm going to skip the details of this proof and just tell you one more thing about product chains. So until now, I discussed the easy case of a product chain where I take a fixed chain and take it to the nth power, and that always has cutoff. But another natural thing to do is to take a sequence of chains that is changing, and for the nth one, to take its nth power. So for a while, I believed that all such examples should have cutoff. Right? So you take the nth power of a chain, but that chain is also allowed to vary with n. So for instance, so one problem I mentioned, but let me officially give it as an exercise. In slightly different notation that I mentioned before. So look at the ZD of, okay, so I'm going to take the say zk of n. So this is going to be this is just going to be a cycle on k equals k of n nodes. So k of n is at least 2, but is an arbitrary number. And then I take then a lazy simple random walk on zk of n to the n has cutoff. So I make no assumptions on this k of n sequence except that it's always bigger than 2. So it could fluctuate. Arbitrarily, and yet, so the point of cutoff, so the formula for the mixing time of the nth chain, depends very much on k of n, but there is always cutoff, meaning, T mix n of 1 minus epsilon over T mix of epsilon goes to 1. So this is an example of chains that change with time, and we take the nth power, and this always has cutoff. But it's not the most general example, and what Laquan showed is that, in general, the best you can say is that any product of n chains has pre-cutoff with factor 2. So, but, so this, okay, so this is true, but maybe it's better to think of, so in this, okay, in this notation, epsilon should be close to 1. But anyway, this is true for any choice of epsilon. And he first proved it for separation, and then it's true also for total variation via the Hellinger distance. So the example that shows that this 2 is sharp, so the 2 cannot be improved, is actually a variant of the Aldos counterexample. So, and I'm not going to give the details on that. So, one thing that I still believe is that if the underlying chains that you take to the nth product are have sufficient entropy, then so there are some sufficient conditions that are still not articulated, which will show cutoff, more general than this case. So there should be a theorem. There isn't yet a sufficiently general theorem that gives so this is, I wouldn't call it an exercise, but more a problem to characterize when if you take some graph Gn and take it to the nth power in the same sense, when this has cutoff. So it always has pre-cutoff, no matter how the Gn change, as long as you're doing lazy chains or continuous time chains. But when it has cutoff, well, in almost all examples, but again, not all. Okay. So the Lacan example, maybe I'm not going to give it in detail right now. And I want to tell you about one more tool to prove cutoff. It's especially useful for separation distance, but can also be used for total variation. And this is the notion of a strong stationary time. So given a Markov chain, we know what's a stopping time. Here we're going to discuss stopping times that can depend on additional randomness. So, for instance, an important kind of stopping time to remember is look at the hypercube example. Remember, we had the lazy hypercube. We had n coordinates, and we chose a coordinate at random every time. I can ask for the stopping time when I chosen all coordinates, right? So that's the coupon collector time. Notice that this is not a stopping time for the this stopping time it is a stopping time, but it's not measurable with respect to the random walk on the hypercube itself. Because if I chose coordinate 3 and then didn't flip it because it's a lazy step, or I chose coordinate 5 and then didn't flip it, there is no evidence in the movement of the chain. If I keep track of where is the particle, there is no evidence in the movement of the particle to whether I chose coordinate 3 or 5. But in the definition of my stopping time, I am looking at which coordinates I chose. So formally, it's a stopping time in an enlarged filtration where we are keeping track also of the coordinates we chose. The key thing that keeps it a stopping time, it doesn't look into the future. So in this enlarged filtration. So that stopping time is an example of a strong stationary time. So what does that mean? So first of all, at the time where it chose all coordinates, in the hypercube, the distribution is completely uniform. But that's even true if I tell you how long it took, right? So how long it takes, it's a coupon collector time. It's tends to be n log n. But suppose I was lucky and I managed, this is very unlikely event, that I chose the first n coordinates I chose were all different. That could happen with a very tiny probability. But even on that event, when I chose all coordinates, the distribution is completely uniform. And if it took less or more time, so that's why it's called the strong stationary time. Contrast it with the notion of stationary time. A stationary time is one where at that time the distribution is uniform, but it's not uniform if I also condition on how long it took. So let me show you an example of a. So here's an example of a stationary time, which is not strong. Choose some node z distributed according to pi, so a random node z with distribution is a stationary distribution, and use tau is just the hitting time of z. So min t so that xt equals z. So obviously x tau, it's equal to z, so obviously it has distribution pi. Okay, but if I know the starting point, say x0 is here, and I choose this z. If I'm told that tau is 2, then I know that the distribution is given that additional information, distribution is very non-stationary. I know that I'm very near the starting point. So there's a distinction between stationary times and strong stationary times. Both can be used for mixing. So there's a very interesting fact that stationary times still bound the mixing time for lazy chains. So this is not at all obvious. So for lazy chains, T-mix, so this is a result of Aldous from the early 80s, that T-mix is lazy chains or continuous time chains. T-mix is bounded by a constant times the expectation of tau. So, and to be precise, let's take the maximum expectation. I'm not writing it, but maximize over the starting point of the expectation of this stationary time. Then the mixing time is bounded by that, assuming laziness. But so that's a non-trivial theorem. There's a much easier theorem, which is at least as useful, which is that strong stationary times bound the mixing time. This is because many natural stationary times are in fact strong stationary. So we saw one example for the hypercube, and we'll see some more. So this is dying. So here is a little argument that bounds the separation distance, so this quantity 1 minus ptxy over pi y, in terms of a strong stationary time. So for strong stationary time, again, one characterization is that the distribution of time tau is stationary and it's independent of tau. So from that you can easily deduce, there's a one-line deduction, that if you have a strong stationary time, the probability that tau is less equal t and xt equals y can be decomposed as a product of this probability and the probability that xt equals y, which will, under this conditioning, which will give you a pi of y. So this is actually an equivalent definition of strong stationary time. Now, once you know that, if I want to look at this difference, so this is just the definition of ptxy, and then we bound above the probability of xt equals y by adding the additional condition that tau less equal t, and then use this decomposition to just get 1 minus the probability of tau less equal t. In other words, the probability that tau bigger than t. In other words, once we have a strong stationary time, we can bound 1 minus this ratio by the tail of that strong stationary time. And notice that this is true for any target state y. The initial state x is fixed here, so when I write p of tau bigger than t, really this, of course, represents this probability starting from x. So we discussed in the hypercube the mixing time in total variation is half n log n. The mixing time in separation actually is n log n. And this argument with that stopping time gives a sharp bound in that case. Now, okay, here we always have an inequality, but in some important cases there is equality here. So what is when do we have an equality? If adding this condition doesn't change the probability. And this is when y is a halting state. So maybe I'll give this definition. So again, Sx of t is the maximum over y of this quantity, 1 minus ptxy over pi y. And the bound we saw 2 slides ago is just that Sx of t is always at most the probability of tau bigger than t. But there are important cases where you have equality, and that's when you have a halting state. So suppose you have a state, so a halting state is a state where, so given a stopping time tau, a halting state is a state that I know, okay, I fix a starting point. A halting state is a state that I know if I hit this state, then the stopping time must have already occurred. So I run the chain, and I have this tau, and a halting state is one where I can't hit it before reaching tau. So again, looking at our canonical example, the hypercube, suppose we start with all ones. So then the all zero state is and our tau is, as I said, the tau is the coupon collected time when we touched all coordinates. Then the all zero state is a halting state because there's no way to reach the all zeros without touching all coordinates. Okay? So once I have a halting state, then the previous argument, just in this inequality, I have an equality because xt equals y means that tau must be less equal t. So this step, which was an inequality, actually is equality. And so we get that this general inequality is, once we have a halting state, it is as an equality. And it means that so we get a somewhat surprising conclusion. If we have a strong stationary time with a halting state, then it is optimal, meaning its tail, so its tail is smaller than the tail of any other strong stationary time. Okay, because for any strong stationary time, we have this inequality holding. And if a strong stationary time has a halting state, then this inequality becomes equality. So it means strong stationary times with a halting state are always optimal.
Sorry, can I ask?
Yes?
Don't you take the maximum over the left-hand side?
Yes. But you can take the maximum. But first, and then you would take the maximum also over the right-hand side. But first, we can look at optimality with respect to a fixed starting state. Yeah. And that's what I'm talking about here. Sx is the maximum over y. Yes. Okay. So
surely if inequality holds and not equality for one y, then won't this mean that you get inequality on the maximum?
So the point is this. So this is always bounded by, right? So the right-hand side here is p of tau bigger than t. So it means that for every y, this quantity is at most p tau bigger than t. If y is a halting state, you have an equality.
For that y.
For that y, but it then means that this y is realizing this maximum, right? Because it's bigger than the value for every other y. Okay?
Sorry, I missed the definition of the halting state.
Okay, so yeah, because I only said it in words, I didn't write it. So y is a halting state. So halting state depends on two things, a stopping time tau and an initial point x. Okay? So the halting state can change according to the initial state. So if the probability starting from x of tau less equal than tau y is 1. So tau y is the first time that the chain reaches y. Okay? Okay, so tau y is the hitting time of y. We start at x, and we want that tau y will be with probability 1 greater or equal than tau. That's the definition of a halting state for tau and x. Okay, so again, in the example of the hypercube, we started at all ones. The all zeros is a halt, y equals all zeros is a halting state for this stopping time, the coupon collector stopping time, and the initial state of all ones. So let me give one famous example of cutoff, which is proved using strong stationary times. So this goes back to Aldous Diaconis from the 80s. And this is top to random insertion. So this chain will be not reversible, so some of our tools disappear. It's not lazy, yet it's very easy to prove cutoff for this chain, just knowing some basics about coupon collector or about sum of geometrics. So what is the chain? We have n cards stacked. Pick a uniform. Take the top card, remove it from the deck, and stick it in a uniform spot. So after we remove the top card, we have n-1 cards, and there are n spaces, because we can put it in the very bottom or at the very top. So there are these n-1 remaining cards define n spaces between them, and we put the card uniformly in one of those n spaces. Okay, so that is called top to random insertion. And it has cutoff at time n log n with a constant of 1. So we'll justify that shortly. Now for the upper bound, one uses a strong stationary time. So here's a strong stationary time. As you put the top card, as you keep running the chain, the original bottom card keeps moving up. And if you think about it, the cards under the original bottom card are in random order between them. So suppose I have, after I inserted, so it might take a while before anything goes under the bottom card. But eventually, so this is geometric with the parameter 1 over n, the time until the bottom card rises by 1. Then after it's already not the bottom card, now it's easier to get cards under it because there are two spaces there. So now it's geometric with parameter 2 over n. But the two cards that will move there, when the second card to move there, it has equally chance to go in each of the two spaces under it. So when I have two cards under the original bottom card, their order between them is uniform. And you can continue this by induction. When I have k cards under the original bottom card, those k cards, if I look at in what permutation they occur, all the k factorial permutations are equally likely. Okay, very easy to check by induction. So when the original bottom card reaches the top position, all the n-1 factorial permutations of the other cards are equally likely. And then I take this original bottom card, which is now at the top spot, remove it, and put it in a uniform spot. So now everything is uniform. So it's a stationary time, and it's even a strong stationary time, because even if I tell you how long this process took, still everything is still true that the distribution is completely uniform. This is a strong stationary time, and it's easy to understand its mean and even its distribution, because again, the bottom card to rise 1 is geometric with parameter 1 over n, because each time you have a chance 1 over n of putting a card under there. Then, so let me write this down somewhere. So tau, this stopping time, which is a time for bottom card to reach top. And then +1, because after that I want to make one more move. So this is a definition of tau. And tau has a distribution which is first geometric 1 over n, plus once it's at height 2, I have geometric 2 over n, and so on. So So the expectation of tau is the sum of these expectations, and this will give and this is going to be very close to n log n, asymptotic to n log n, and also you can check, for instance, by Chebyshev or by more refined ways that tau is concentrated so around n log n. So the variance of tau is, you can sum the variances, so it's order n squared. So tau will vary by about n from n log n. So it's concentrated near n log n. So this means that if I wait slightly more than n log n, with very high probability, tau will have happened already, and hence we will have mixed. So now, although there is no official collecting coupons here, observe that tau is exactly, except for this, tau is exactly the coupon collector time, because if you think of the coupon collector time to collect the first coupon is 1, the next coupon is geometric n minus 1 over n, and so on. So the coupon collector time has the same distribution, except you have to sum it this way instead of this way. Comment? Okay. So this is a strong stationary time. Is it optimal? Or can you come up with a better strong stationary time? Okay, I'll answer this one, but the next question I expect you to answer. So it's not optimal. There's a better strong stationary time. So instead of waiting for the bottom card to reach the top and then make one more step, let's look at the second from bottom card. Okay, so this is the card that started in the second from bottom position. Wait for it to reach the top and then do one more step. So of course this will happen earlier, strictly earlier. Okay. So if I look at a new stopping time, tau tilde, which is the first time, so that a second from bottom card reaches top, +1. So this is strictly smaller than tau. But it's still a strong stationary time, because it's also true for this one that the cards under it are in a uniform random order. So initially, under it, we have the bottom card. But then the next card that comes in will come in either on top of the bottom card or below the original bottom card. So the fact that these cards are internally in uniform random order remains true for this case. So this tau tilde is better. Okay, so can you think of a strong stationary time that's even better than this?
At this time, the deck will not be uniform yet.
This time it will be uniform.
Even
So
though the bottom card does not have time to reach the top.
So So again, so the bottom card could reach the top. It allows for it because, I mean, yeah. Now the bottom card, for the distribution to be mixed, the chance for the bottom card to be at the very top should just be 1 over n. It shouldn't be larger than that, and it is 1 over n because, as we said in before the last step, the original, the second to bottom card will, when it reaches the top, the distribution under it is uniform. So of the other cards. So the original bottom card could be, with probability 1 over n minus 1, it could be right near the top. And then we just need this current top card to go to one of the locations under it, which is another factor n minus 1 over n. So the chance the original bottom card will reach the top is exactly 1 over n as it should be. So this is a strong stationary time. But I'm asking, is it optimal?
Well, there is a halting state for it. If you just fix some state where the second to bottom card is below the bottom card, then this is the halting state.
That's right. So we have really bright students here. So thank you. So okay, so let me repeat this. So we look at this, the two cards, the original bottom card and the original second from bottom, are going to rise together and retaining their order until the original second from bottom is moved. So until this time tau tilde. So any state, you can name any state you want where the original second from bottom is below the original bottom. Any state like that is a halting state for this tau tilde. So it means we don't have to search to see, okay, can we define in some other clever way a better stationary something? No, we're done. This one is optimal, and it's optimal simultaneously for all t. So it optimizes the tail for all times together. So this is not obvious that you have a strong stationary time, which is at the same time optimal for all t. One thing I should comment, there is a theorem of Aldous and Diaconis that says even when you don't have a halting state, so sometimes there is no halting state, but there always is an optimal strong stationary time. So there always is one that achieves where the equality so let me get back. This is almost dying. So equality here holds whenever you have a halting state, but but sometimes there is no halting state, and maybe I can give another exercise. A fine chain so that every strong stationary time has no halting states. So I think there is such a chain with 3 or 4 states. So you don't have to look for very big chains. However, in many examples there is, and then it's very useful. Okay, I'm going to.
Excuse me.
Yes.
So all of this depends on x. So
Yes.
what's the exact formulation in terms of x?
So So let's just fix x. So for fixed x, which is the starting position, every strong stationary time has no halting states. Okay, I could talk more on cutoff, but let me stop this for now because I want to start telling you something about the other topic announced of this theory of this course, which is rates of escape. So a lot of what I'm talking about in this part of the course you can find in chapter 13 of this book. So this is a book with Russ Lyons that was just finished this year after some 25 years of work. It's available both from Cambridge University Press and online on Russ Lyons' webpage. You can find the online version. And this is actually Hugo's copy, so you can go look at it in his office if you're staying around. And I know Jean-Francois has a copy as well. I wish I could bring you all copies, but the carry-on, doesn't. The plane would not take off, So it's 700 pages. So anyway, so here's a little proposition about mixing, which involves a rate of escape. So consider let's say a lazy simple random walk. So it could be actually lazy or not lazy on because I'm doing a lower bound on a graph G of n nodes. Then there is a bound for the mixing time. So okay, then for any epsilon less than half, if n is large enough, then T mix of epsilon is bigger than the diameter of G squared over a constant log n. So contrast this with the trivial bound, which says that T mix of epsilon is bigger than the diameter of G over 2. Okay, so the trivial bound follows because if I have two nodes x and y that achieve the diameter, so the distance. So when I talk about the diameter, I'm talking about the graph distance. So the distance from x to y is the number of edges in the shortest path between them. And then the diameter represents the distance, the largest distance in the graph. So we suppose the graph distance in G between x and y equals d, which is the diameter. And then if t is less than the diameter over 2, then it follows that if I look at the distribution from x and from y, right? Their total variation distance is maximal because one is supported on the vertices that are closer to x than to y, and the other is supported on the vertices closer to y than to x. So this total variation distance is just going to be 1 for all times. And it means that the d bar metric, so d bar of t is 1, but d of t is bigger than half d bar of t. So remember, d of t is the distance to stationarity, maximal distance to stationarity, while d bar is the maximal distance from two nodes. So it means that the total variation distance to pi is at least a half. Okay, so that's the trivial bound. But here, now the trivial bound is sometimes sharp. For an expander, the diameter is log n, and the mixing time is order log n as well. So, but if we're talking about bounded degree graphs, which are a lot of the graphs we care about, then the diameter is at least log n, and then this bound is at least as good as this. And often it's much better because in many graphs we know the diameter is much, much bigger than log n. And then this would be better. It also hints at the importance of diffusive estimates for random walks, much more general than random walks in RD that we are familiar that have this diffusive behavior. So behavior, the fact that time to reach distance r is often about r squared is much more general than we are used to. And this is one example of that. Okay, maybe I'll put greater equal. Now, the way we'll prove this is from a very general and famous estimate, which should be even more famous, and that's the Varopolous-Carne bound. Which has many applications. I'll show you several of them. So Varopolous-Carne bound, yes, it's called the Varopolous-Carne long-range estimate, or long-range bound. It says that this is from 1985. Now this is not a joint paper. There was a first paper by Varopolous that proved a slightly weaker version of the bound, and then in the same year, motivated by that, a kind of almost optimal version by Keith Carne. So these are two separate papers. And what they proved is the following. So if for a reversible chain, it's all right, pi p. So pi is a stationary measure and p is the transition matrix, which can be finite or countable. And let's make it let's make it irreducible. So then this can be dispensed with. So again, I remind you, reversible means that pi of x pxy is pi of y pyx. And I'm going to write pxy, sometimes small p, sometimes big P. It means the same thing, just a transition probability from x to y. So that's reversible. And then the inequality says that ptxy can be bounded as follows. So square root of, so there is a less important factor in the front, this ratio of transition probabilities with square roots, and then an important factor let me write it and then explain. So 2 root pi y over pi x e to the minus distance squared from x to y over 2t. Okay, now, well, the right-hand side, it's clear what it means. This is, and you see a Gaussian tail. And note, there is no, this is not in ZD, it's completely general setting. And what is here, so ST is a simple random walk on the integers. Right, so we have this completely general reversible chain, and we can bound the individual transition probabilities at time t by the probability that a simple random walk on the integers, the most friendly object, has gone distance bigger than dxy. So what is dxy? So given a reversible chain, we always have a graph where we connect x and y if we can go in one step from x to y. And reversibility means that this graph is undirected. If we can go from x to y, we can go from y to x. And so this is the graph we work with, and the distance is just the graph distance here. An equivalent description of a reversible Markov chain, you can just start with a graph, put weights on the edges, and walk with probability which is proportional to the weights. So every reversible Markov chain can be described this way, and this always yields a reversible Markov chain. Okay, but so dxy is distance, graph distance in this graph of allowed transitions. Okay, any questions about this bound?
Is there any continuous analog to this bound for heat kernels?
Yes, in fact, I'm not going to go into that, but you're encouraged to look in the original Varopolous paper, because what Varopolous did, he took a graph, he took every edge of the graph and replaced it by a pipe. And this way he obtained a manifold. And then he proved that if the pipes are thin enough, random walk on the graph is well approximated by Brownian motion on this manifold. And then he used a continuous version of such inequalities on this manifold to deduce the graph inequality. And there are other, so in continuous time, there are actually more variants of this that I won't go into. But what Carne realized is, so of course, in doing these transitions, he lost something due to approximation errors. And then what Carne realized, what's the correct discrete analog of this continuous argument, and that's the proof I'll show you later. Okay, now, the second inequality here is just the standard Bernstein or Chernoff bound for simple random walk. It says, the Gaussian upper bound for simple random walk. So you can you can look this up in Wikipedia or wherever you like. So this I'm going to leave either you know it, or it's an exercise to verify it or look it up. So going from, so this is just an estimate for simple random walk on integers, the probability it goes far. So you get it just by looking at the moment generating function of the simple random walk. So of course this is not new to these 85 papers. This is 80 years earlier or so. But so this is the inequality proved in these papers. So let me. So we'll see a proof of this. But let me first tell you, how does it imply the mixing time bound I wrote down. It's very easy. Draw. So again, start with the same picture. Find in the graph. So this application is for finite graphs, since I'm talking about diameter. So find find x and y that realize the diameter. So the distance between x and y is capital D, which is the diameter. Look at the set A, which are all the points z, so that the distance from x to z is at most d over 2, and observe that for every z in A, the distance from y to z is going to be at least d over 2. Because otherwise you'd get the contradiction to the triangle inequality, right? If the distance was strictly less than d over 2, then you'd get distance from x to y to be strictly less than d. Okay? So, and the distance from x to y is d. So we have that. Now, so for every z in A, what can you say about, so Ptyz is less than, so we use that bound. So so we're talking about the graph. So here I should have emphasized, right? So this is a lazy or simple, or so it's true both for lazy and non-lazy simple random walking graph. Pi is the same, it's just given by the degrees. So the largest possible ratio of pi y over pi x is going to be root n. So every vertex has degree at most n and at least 1, because I'm talking about, so okay, I should have, so when you talk about the graph, I didn't say, I want it to be connected. So my chains are irreducible and the graphs are connected. So add the word connected, otherwise mixing time doesn't even make sense. So it would be infinite. So the graph is connected, and so this ratio, root pi y over pi x, is at most root n. And then we have this e to the minus. The distance of xy was the diameter over 2. So we get d squared over 8t. So now, if you plug in t, which is the diameter squared g over 16 log n. So to be precise, you have to put integer parts. I'm not writing them down, so you can add them as needed. So, but if you plug in this choice of time into this formula, right? So this is just d squared over 16 log n. So the d squared will cancel, and so this will become e to the minus 2 log n. So overall, this will be n to the minus 3/2. And I omitted the 2. Okay, so there's a 2 and a 2. Okay, so in other words, the transition probability from y to A is going to be less than 2 over root n, because the size of A is at most n, just sum over c. On the other hand, so the same argument gives that the transition probability from x to A complement is also less than 2 over root n, because anything in A complement has distance bigger than d over 2 from x. So it's exactly the same argument, gives us this bound. And now if I look at d bar of t, it's bigger than the distance pt xa minus pt ya. So it's bigger than 1 minus 2 over root n minus another 2 over root n, right, just by these inequalities. So 1 minus 4 over root n. So you see that this is going to be close to 1 provided n is large. So d of t is going to be bigger than half of that, so half minus 2 over root n. And so you see that for any epsilon less than half, you have if epsilon is strictly less than half and n is large enough, we get this inequality. Okay, so we'll start next class with a proof of a Varopolous-Carne inequality. The shortest proof, which is the original Carne proof, is a surprising use of Chebyshev polynomials. And the nice thing is it uses Chebyshev polynomials, but you don't need to know any theorems about Chebyshev polynomials. Just the definition of Chebyshev polynomials does the work. It's quite remarkable proof. I would say that in some 30-something years of doing mathematics, this I would say is my favorite theorem. It's not my theorem, but the theorem I like the most because it's so useful, and I'll show you several applications, and the proof is so beautiful. So you'll see it in the first 10-15 minutes of the next lecture. And then I'll show you one more application to random walks on groups. So so this application was already described in Varopolous' original paper, that a random walk has positive on a group. So think of an infinite group. There's a version for finite groups as well. It has positive speed if and only if the entropy grows linearly. So the non-trivial direction of that follows from this inequality. Okay, so we'll continue tomorrow.
Other questions?
So you said before that you could bound the mixing time by the expected time of a stopping time, of a stationary time.
Right.
It doesn't have to be a strong stationary time.
Yes.
Could this also work if you have like an almost stationary time? So
Yes.
Okay.
Yes, it also works if it's almost stationary, provided the chain is either lazy or continuous time.
Other questions? If not, thanks again.